Hello and welcome. We are going to be starting a new topic, Riemann integration. So Riemann integration is super important, right? And there are a lot of theorems and it's weighed really heavily. But before we can even get into any of the big things with it, we have to sort of start off with some of the basics. Okay, introduction to what a Riemann sum is. So we're going to define it and I'm going to build up an intuition surrounding it. So I'm going to start with this specific example of approximating the area of a circle. We're going to have two methods of approximation: inscribing a polygon, an n-sided polygon inside the circle, and circumscribing this n-sided polygon, right? So we may wish to find the circle's area by squeezing the circle between two n-sided polygons and taking the limiting process as n increases, right? For greater values of n, the inscribed polygon increases in area. Okay, so the inscribed polygon will increase. So when it's a triangle, it's the smallest, and when it's, infinitely large, it's gonna reach its not max, but supremum, but we'll talk about that. So, and the circumscribed polygon will decrease in area for greater values of n. So those two are increasing and decreasing, right? And they're bounded above or below, respectively, by the actual area of the circle, right? The method of inscribing will always underestimate the area of the circle, and circumscribing will always overestimate, right? And these bounds, specifically the circle, also happens to be not just any upper bound, but the least upper bound, and not just any lower bound, but the greatest lower bound, right? So, more importantly, as we take larger values of n, the approximation gets better and better. And as n approaches infinity, the areas of the inscribed and circumscribed polygons converge to the same value. And that value happens to be the area of the circle as we know it. And we're going to apply a similar method, right? And hopefully, you can keep this example in mind when we're doing some of the things in this video for plane region stuff. So let's say we have this function, right? Defined from the closed bounded interval a comma b, right? F. So let's say we want to find the area of the region contained by the x-axis, the line x equals a, x equals b, and f, okay? In other words, we want to find the area of which region? This region, okay? We want to find this area. So how are we going to do it? Well, one way that may think to do it is to approximate the area using rectangles. This is one approximation, right? Notice some rectangles under approximate and some over approximate, but we don't have a very precise approximation necessarily, right? It's kind of wacky and it's not very precise, but it gets the job done for a rough approximation. And we're going to do the exact same thing with our polygon. We're going to increase the number of rectangles. And now notice how our approximation gets better, right? The error, which is difference in the actual area and the rectangles, or the actual area intuitively, right? uh, is getting smaller. And as we take in even thinner rectangles, it gets even better. So the idea is as we take more and more rectangles, right, we should get hopefully a more precise area. And if we take such a limit, we should get the exact area. All right, and then building up the intuition, but I'll talk about that in a bit. First, we're going to define a partition P of the interval a comma b, and we're going to denote it like this. So it is an ordered set, so order matters, of the form um, x naught comma x1 comma x2 comma dot 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 all the way up to x sub n. And these are the endpoints of intervals, right? They form these partitions, right? Specifically, any x sub I is less than x sub I plus 1, right? So this partition forms subintervals, these subintervals, okay? If you look at this graph, each rectangle kind of corresponds on the x-axis, right, to some subinterval. This is a subinterval right here, x I and x sub I plus 1. This is that subinterval, right? And those endpoints form are a part of the partition, right? Now, one method, which is what Bernard Riemann first used, right? This is his original definition, is that to choose any partition of, of the interval, right? That is to say, choose any, split it into any amount of subintervals with any arbitrary length, it doesn't matter, and more particularly tag any point in of outputs in that subinterval, right? So we can make basically what Riemann was saying is that we can choose any rectangle inside the graph, right? Um, which is what the tag partition is doing, right? Um, and what that is, which is what he suggested, is that if we take any, partition, and more specifically any tagged partition, okay? So let's say in this interval, right, in this partition specifically that we're looking at here, we take any value of f. It could be here, it could be here, it could be here, it could be here. Doesn't matter. And we form a rectangle there. As long as the longest subinterval, okay, not just n goes to infinity is simple. We need to take the length of the longest interval, and as long as that goes to zero, right? As long as the length of every single interval goes to zero, right, approaches zero, that will give us what we know as the Riemann integral. However, we will not be studying that because that is very difficult to compute and very difficult to prove. So instead, we're going to be studying with some of the Darboux integral, if I pronounce that correctly. But it's, believe it or not, it's equivalent. So we'll just say Riemann integral. But it's a separate definition, but it's equivalent. Like if a function is Riemann integrable, or sorry, if and only if it's Darboux integrable. So rather than choosing any rectangles in any tag partition, we may choose to, just like in our circle example, create an overestimation of our area and an underestimation. And so long as we take the limiting process, these should both converge to the area we're looking for, okay? As assuming it is Riemann integrable. So in any subinterval, we may choose to take the maximum value of f and form a rectangle that's completely above f. And similarly for the minimum and a rectangle completely below, right? This is our overestimation and our underestimation. But only in a continuous function need it attain a max and a minimum, right? By the extreme value theorem. It's possible that there's a bounded but discontinuous function that does not reach them, right? That we don't have a max or a min. So to extend our idea, we're just going to generalize it and use the supremum and infimum, but we should have the same exact idea. And we're going to use the following notation. Let S sub I denote the supremum of f over a subinterval from x sub I to x sub I plus 1, and t sub I similarly for the infimum of f, right? That's like the minimum value, sort of, but f doesn't actually have to attain it, right? Um, that's one way of thinking about it. I'm not going to define it. I've talked about supremum and infimum before. But that's just one way of thinking about it, right? Like extending max and min so that it doesn't have to like touch it and like attain the value, but it is the lowest upper bound or greatest lower bound. So notice this is what we're doing, okay? This is what I mean by our overestimation or underestimation. The upper rectangle is in pink, right? And don't get confused. This whole rectangle, right? We're talking about the whole rectangle, which is in pink. It overlaps, but it's the whole rectangle that we're considering. Notice it is always above, right? That area of the rectangles will be greater than the area of the region, okay? And we do consider the signed area, right? If it's below the x-axis, our area is negative. Okay, so notice that this blue region is completely an underestimation, so it's inscribed, and the overestimation is, you could say, circumscribed, right? So notice how the rectangles are. And more importantly, when we flip it on the other side now, our overestimation becomes inscribed and our underestimation, right, becomes circumscribed only because of the sign issues. But this should give you an idea of kind of the approximations we're doing, right? And we can compute the area of the upper rectangle as S sub I, right? Because that's the height times the width, which is the length of the subinterval x sub I plus 1 minus x sub I. Similarly, for the lower rectangle, just using the infimum, right? So we can now define what an upper and lower Riemann sum are, or an upper and lower, right? So finally, for any partition, right? Any partition, right? And remember, any partition is just any way of sort of splitting the any interval into multiple subintervals, like choosing certain endpoints. That's any partition, right? No, not a specific one necessarily. All right, we can define it to be the upper sum is just the sum of all the rectangles, right? The index start at 0 because we said a is x sub 0 and goes all the way up to n minus 1, right? You see x sub n minus 1 here, right? Because we don't actually consider b, there's no rectangle after. So we go from I equals 0 to n minus 1 of the area of the upper rectangles, right? Remember, we already showed this is that area. We're just adding up rectangles. Similarly, for the lower sum, we're adding up the rectangles. That's all we're doing, so don't get confused with this notation. And we're going to prove our first case, right? Which should be, if we can prove this, we've proven some sort of consistency, right? Because we know the area of a rectangle, right? We've defined it, and we're going to hopefully show that for a constant function, if we compute the upper and lower sums, we do get our traditional area. So since f is constant, whatever k is, which is f of x, is just the supremum and the infimum. So the upper sum, you should notice, is equal to the lower sum. And when we compute it, factoring out k, we get a telescoping series, which telescopes to x sub n minus x sub 0. But remember, we said x sub n is defined to be b, and x sub 0 is defined to be a. So we have k times b minus a. And looking at it graphically, although I don't have one, I could sketch one up pretty quickly. If we look at the graph, right, and this is what f of x is equal to k. Obviously, from a to b, we just want to multiply by this height k times b minus a, and that gives us our area of the rectangle. Okay, so this is consistent, right? What we did makes sense. And now about this. Now we're going to be doing the nth standard partition, right? This is our standard partition. So while we can study any type of partition, we're going to study specifically standard. This is the easiest one to work with. And it's simple. Basically, we're going to split the interval a comma b into congruent segments, n of them, right? So let me show you before I give you the definition, right? We're going to call this little thing delta x, right? And it's b minus a over n. Um, and basically, what it is that we're taking this length, which is congruent in all of them. We're starting at A and we're adding delta x to each one to get what we were looking for. For example, um for any x sub I, right? We have A plus I times delta x, right? We're just adding delta x I times to A, and that's A plus B minus A over n times I. So that's how we can define a standard partition, okay? So all I'm doing is I'm rewriting what I just showed you. And that's what a standard partition is. Remember, we're just splitting it into congruent segments. And also notice that for any I, the length of the subinterval is what we said is delta x. It's b minus a over n. Now we say our upper sum with the standard partition in mind, right? Because remember, in order to have an upper sum, we need a function and we need a partition, okay? So with the standard partition in mind, this sum becomes as follows, right? And because we already said the length of each subinterval is the following, and also, of course, b minus a over n is constant in terms to the index of summation, so you could factor that, or sorry, you could take that out of the sum. Again, like I said, similarly for L. And here is where I give you a disclaimer. I kind of talked about this a bit, but for these videos, I will only consider the standard partitions of an interval and the Darboux integral. Sorry if I'm mispronouncing it. Further analysis is going to be beyond this course. If we want to talk about any tagged partition, which is the Riemann sum, no, that's beyond this course. If we want to talk about the Lebesgue integral, definitely beyond this course. Um, and if you want to talk about non-standard partitions, it's not necessarily beyond, but it's a lot more time consuming, and I'm not going to go over it. So here's an example problem that should build up some more intuition for what we're going to be doing. So compute the infimum and supremum of the upper Riemann sum of f over the standard partition of 0, comma 2, and the supremum of the oh, sorry. So the infimum, okay, the infimum of u, and this one should be the supremum of L, okay, of f on the standard partition, okay? But which function? X. This one should be easy kind of to work with. And I'm just gonna go through it and I'll leave the lower one. I'll give you the answer, but I'll leave that as an exercise. So for the upper Riemann sum, what we're gonna do is b minus a over n times this sum, right? So for the upper sum, we're gonna have this. So b minus a over n times here we're just plugging in the formula we already know, right? Now the supremum x is increasing, right? Over the entire real numbers. Maybe you remember the graph, maybe you remember monotonicity, derivatives, all those theorems. Here's where it comes into play. X is increasing, right? So its maximum value on any interval will be the right endpoint, which is x sub I plus 1. And from here, you apply your summation rules. And remember, x sub I, we said all the way up here what x sub I was. We're going to plug in our a and our b minus a, right? And we're going to get 2 over n times I. And you should know your summation rules, and you should get 2 plus 2 over n. Now, I'll leave it as an exercise to you to determine why the lower one is 2 minus 2 minus 2 over n. The important part is that both the supremum and the infimum are 2, right? The reason why, I mean, it makes sense. You could think about it a bit, but the upper sum, okay, well, 2 definitely happens to be a lower bound, right? All these values are just adding on positive numbers to 2, so it has to be all of them greater than 2. And 2 is the greatest lower bound, because if there were any lower bound greater, you can reach it, right, by choosing sufficiently large n. And same idea for L, just flip. So the supremum and the infimum are equal. And we're going to use the supremum and the infimum when we're talking about what integrability is, more specifically the Riemann integral, or Darboux, more technically. So here we go. This, don't get confused with the notation. This is like, I'm not gonna go too far in the notation, but this is like an S kind of, but like this. You put A here is your lower sum of integration and your upper sum of integration. And here, if we taking a lower sum, we put this bar here, and if we're taking an upper sum, we take this bar here. And if not, then we don't put any bars, and we could just put f or f of x, and dx tells us what variable we're integrating in respect to. It's not multiplication, although a lot of textbooks use kind of the notation in a wishy-washy way. It's not multiplication, it's a notational choice, okay? We could also denote it like this. You see, it's a notation. So we define the lower Riemann integral, right? The lower integral as the supremum of the lower sum, right, of f over on a standard partition for n natural numbers, and similarly for the infimum and the upper sum, right? And now we can say f is Riemann integrable, or just integrable for now, which is the same as saying f belongs to, this is the notation, the set of Riemann integrable functions on the interval a comma b, right? This is the notation just saying f is integrable over a comma b, if and only if these two, right, match. Remember up here we said these two match. That's saying yes, f of x is equal to x is Riemann integrable over um the interval 0, comma 2. Right. And believe it or not, this is not technical because remember, like we said, I'm using the standard partition, which is less general, but this holds also for any partition, right? And now we can define what the definite integral is. And now, assuming that the function is Riemann integrable, that the condition is met, and we can define just the normal integral to be just either one, right? They're both equal. And up here now that we know what we're doing, we know now that the integral from 0 to 2 of f of x dx, which is the infimum or the supremum of the upper or lower sums, respectively, of f with standard partition on the integral 0, comma 2, so mouthful, is equal to, and f of x is actually equal to x, is equal to 2, right? You may also notice that if you do geometry and you calculate the area using the triangle, you will get 2. Or later on, when you use the fundamental theorem of calculus, you get 2. So yeah, that checks out. And I'm gonna do a bit more, but this is more important for next video. So I will reiterate this next video, but if both the lower and upper integrals are real, then um, they are equal if and only if their difference can be made than any positive epsilon. This is one of the, I think, lemmas I discussed. If you can make the distance between any two numbers arbitrarily small, the numbers are equal. As well, this is another remark. The lower sum, right, which is, of course, less than or equal to the actual, like, the supremum of the lower sums, right? It's an upper bound. And this one's a bit, it's not hard, it's like trivial, but it is like a lot to write that this inequality holds. And again, this inequality is obviously true, but you should know this series of inequalities because we can apply it here by saying that if we can make this difference less than epsilon for all positive epsilon, then we can imply this difference is less than epsilon, and so we've shown that this is enough to show that a function is Riemann integrable, right? Um, and finally, really quickly, this is actually a reiteration without absolute value because it's positive, right? Upper is always greater than lower. This is exactly what I'm saying. F is a Riemann integrable on a comma b if and only if for all epsilon greater than 0 there exists a partition or there exists an n in the natural numbers. It doesn't matter. Um, with the specific partition such that the upper minus the lower can be made less than epsilon, right? All right, and the reason why I did this last part was to build up for next video where I actually start proving some theorems, starting with all continuous functions are Riemann integrable. So hopefully this helped you out building the intuition and the definitions using the Darboux integral. And just note Riemann and Darboux are equivalent, right? It's not like the Lebesgue integral where they're not equivalent and one's a stronger integral. No, they're the same thing. So hopefully keep these definitions in mind and try to memorize them because you're going to be using them when evaluating integrals for the very first time. So good luck and have a nice day.